Welcome everybody. This is the third tutorial of the Restart Tutorials on Telecommunications series. And we have the pleasure to have with us Antonio De Maio and Massimo Rosamilia. Antonio is a full professor at the University of Naples, Federico II, and Massimo is assistant professor also there. They are experts of signal processing, and the topic of today is waveform design for coexistence between radar and communication systems from theory to experimental validation. So it's an interesting topic associated to one of the most important research directions that we are exploring within Restart. So I'm sure it will be of your interest. So Massimo and Antonio, you can start. Thank you.
Well, distinguished colleagues, friends, students, good evening. It is my pleasure to be with you today and give this tutorial on waveform design for coexistence between radar and communication systems, from theory to experimental validation, of course, together with my colleague, Dr. Massimo Rosamilia. Please, before starting, let me thank Professor Antonio Capone for the kind and appreciated opportunity. Here we can see an outline of this presentation. First of all, we will see some motivations for the problem. Then we will go through the analytic formulation of the waveform design process. Hence, we will see something about the performance of the technique, together with a discussion on extensions and connected issues. Then something about the experimental validation, the concept of cognitive jamming and for spectral coexistence will be illustrated by Max. And finally, we will draw some conclusions and we'll see some possible future research avenues. First of all, something about the motivation of the problem. Well, it is well known that coexistence between radar and telecommunication systems over the same spectral bandwidth is currently one of the hot research topics, both in communication and radar communities. This is because the RF electromagnetic spectrum is a limited natural resource, which is necessary for an ever-growing number of services and systems, such as mobile communications, radio and television broadcasting, and of course, for remote sensing. Moreover, both high-quality, high-rate wireless services and also accurate and reliable remote sensing capabilities, they call for increased amounts of bandwidth. And on the other hand, there are some basic electromagnetic considerations, such as good foliage penetration, low path loss attenuation, and also the size of the devices. And these considerations push the systems to coexist in the same frequency band. As a result, I would say that together with oil and water, the RF spectrum nowadays represents one of the most important and also critical commodities due to the huge impact that radio services have on the society. And here we can see a famous sentence by a very famous and also extremely respected colleague, Dr. Mike Weeks, from United States Air Force Research Lab, who unfortunately passed away recently. And this sentence is about the spectral congestion problem. And he claimed that the desire to autonomously anticipate, find, fix, track, target, engage, and assess anything, anytime, anywhere in a spectrally dense environment will require changes on how to build, modify, and deploy radar and radio frequency systems. Actually, Dr. Mike Weeks immediately recognized that the mentioned RF spectrum congestion problem calls for new sensing methodologies capable of enabling a smart and efficient spectrum utilization, accounting for the time-varying behavior of the emitters in the operative scenario. And in this context, it is mandatory the design of advanced radar signals, ensuring compatibility with surrounding electromagnetic radiators. I mean, they should be able to keep acceptable the interference induced on frequency overlaid systems. Here are some examples where the spectrum congestion is a serious concern. Radars that perform ground foliage penetration or take advantage of ionospheric propagation to look beyond the horizon, they tend to operate in frequency intervals below 1 gigahertz, typically HF, VHF, and UHF frequencies. And in these bandwidths, also other spectrum users exist. And these systems must therefore take measures to identify and also avoid such interference, or to employ cancellation techniques to reach a noise-limited condition, or I would say at least as close as possible, a noise-limited condition. Another area of current concern to radar users is the allocation of spectrum to communication systems such as the WiMAX, the LTE, the 5G, in the S-band portion, which is also adjacent to the allocations for air traffic control in maritime radars. And also, there's the United States National Weather Service Next Generation weather radars. They operate in frequency interval around mid of the S-band. Here we can see a list of situations where bandwidths are impacted by communications, for example, at S-band, 5G, 4G, and fixed wireless access are being considered for sharing. At C-band, we can see that wireless local area networks and unlicensed user may get the primary status. Also at X-band, we have fixed and mobile users that can be given a co-primary status. And also in the Ku band, we have another example. If not carefully addressed, the joint presence of multiple emitters on the same frequency interval can determine serious impairments in the final radar product. And here we can see an example with reference to synthetic aperture radar processing. On the top left figure, we can see a range compressed SAR image. These are real data collected in November 2001 in Grumento area, which is in south of Italy. And the sensor was mounted on board a Cessna aircraft. And you can see in this figure that there are some interference lines for some azimuth that they cover almost all the ranges. And without taking care of them, in the focused synthetic aperture radar image, there are some unwanted horizontal strips. You can see them here. And they actually are byproducts of this form of interference. Of course, if these mentioned interference lines are detected through a bespoke algorithm, and then a cancellation algorithm is used, a much better image can be obtained. You can see it here in the bottom part of this slide. Well, let us now start with the development of waveforms enabling radar operations in spectrally crowded environments. First of all, it is fundamental to formalize an appropriate system and signal model. In this respect, we consider a monostatic radar system, which transmits a signal composed of capital N subpulses, whose fast-time code vector is denoted by C. It is an n-dimensional complex vector. Each entry of C weighs a delayed version of a basic subpulse, or also chip. And at the receiver side, the incoming signal is first of all down-converted to baseband, then it undergoes a subpulse matched filtering process, and finally it is sampled at the chip rate. This leads to the fast time observations from a range azimuth cell under test, and they can be arranged in a vectorial form in the vector V, which can be written as the product of alpha times the code C plus a component N. And in this notation, alpha is actually a complex parameter accounting for the echo from the target within the range azimuth bin under test. And the vector N, it contains the samples of the filter disturbance. It is modeled as a zero mean, circularly symmetric Gaussian random vector with the covariance matrix equal to capital N. It accounts for white internal thermal noise, licensed communication signals sharing the same bandwidth, also jamming, hot clutter, and so on. As to the licensed RF systems coexisting with the radar of interest, we assume that each of them operates over a specific spectral bandwidth, which is denoted by omega k, whose knowledge relies on radar environmental cognition, as we will see later in this talk. And to guarantee spectral compatibility with these systems, the radar has to adequately shape its transmit waveform so as to control the amount of interference which is produced on the shared frequency bandwidths. This is tantamount to forcing the radar probing signal to comply with the following quadratic requirement, the one which is shown here in the slide, where the matrix Ri depends on the spectral characteristics of the overlaid systems. The weights Wk are assigned to each licensed bandwidth, I mean to each licensed radiator, and the weight K rules the importance of the different RF systems, and finally EI indicates the overall amount of interference level which is allowed. It is important to observe that both the weights and the maximum interference level depend on the spatial location of the RF systems, in addition, of course, to the demanded quality of service. Sorry. And according to the previous discussion, it is also evident that to control the amount of interference which is induced on coexisting telecommunication networks, the radar needs to know the number of coexisting licensed radiators, their bandwidth, and also the penalty weights to assign to each competing system. This information can be acquired via a radio environmental map, which represents the key to gain spectrum cognizance and is at the base of an intelligent and agile spectrum usage. A radio environment map can be regarded as an abstraction of the real-world radio scenario. It is substantially an integrated database, digitizing and indexing all the available electromagnetic information. The figure that can be seen here in the slide, it illustrates some multi-domain knowledge sources which are contained into a radio environment map. They are, for instance, geographical features, available service and related spectral regulations, modulations, techniques used for access to the channel, the activities of telecommunication networks. Some telecommunication systems can be turned on during the morning and they can be turned off during night. Also, previous radio experiences and measurements. The idea is to store and process a variety of data so as to make possible the inference on a multitude of environmental characteristics, such as the location of transmitters, propagation conditions, estimates of spectrum usage over space and time, and to populate this radio environment map, both a priori knowledge as well as spectrum sensing techniques can be adopted. In particular, in the right part of this figure, you can see a dedicated sensor network that can be used to gather fresh information and to update and improve the quality of the scenario, of the electromagnetic scenario. And let us now present the objective function and the constraints that are involved in the radar waveform design. Our goal is to boost the target detection probability while controlling both the amount of interfering energy produced in the shared bandwidths and also some important features of the transmitted waveform. To this end, we consider as a figure of merit the signal to interference plus noise ratio, which is reported here in our slide, and it is a quadratic form. Here, the matrix R is the inverse of the interference covariance matrix. And we know that the target detection probability is a monotonically increasing function of the SINR. Then we force some constraints on the transmitted signal. In particular, we consider an energy constraint to comply with the radar power budget. And also, we impose a similarity constraint with the prescribed waveform so as to manage some relevant features of the radar signal. In other words, we are forcing our waveform to lie in a ball which is centered around the nominal radar signal and whose size influences the degrees of freedom in our optimization. The larger the ball, the higher the number of degrees of freedom that we have in our optimization. There are several reasons that motivate this constraint. In fact, in uncontrolled optimization can lead to signals with significant modulus variations, with a poor range resolution, with high side lobes, and more general, we can experience an undesired ambiguity function response. And all these drawbacks can be at least partially avoided, forcing our solution to be similar to a non-radar waveform C0 which shares some nice properties such as constant modulus, reasonable peak to side lobe level, in general a reasonable ambiguity function. And finally, to guarantee the spectral compatibility with the overlaid radiators, it is necessary to provide a control on the overall interference energy produced in the shared bandwidth, and substantially we are forcing the constraint, the last one that we have discussed before. Summarizing. The waveform design problem of interest can be formulated as a non-convex, quadratically constrained quadratic optimization problem, P1, which is shown in the slide. And as already highlighted, this is a non-convex optimization problem. Maximization of the SINR, and here we can see all the constraints that we have discussed in the previous slide. Well, before proceeding further, it is worth pointing out that the similarity and the spectral constraints are in general competing requirements. In other words, not all the pairs EI and epsilon, they lead to a feasible waveform design problem. As a consequence, it is fundamental to characterize the feasibility of the problem P1 is a function of EI and epsilon for any similarity waveform C0. This observation leads to the definition of the interference similarity achievable region, which is associated with the reference waveform C0, and it is formally defined in the yellow box, which is here in the slide. It is the set of pairs that lead to a feasible optimization problem. And studying the set F, it is possible to prove two interesting properties. First of all, the interference similarity achievable region is a convex set, and this means that from a practical point of view, we can control its accuracy description, and second, each point on the boundary region can be computed in polynomial time. As a result, the radar designer can select the most appropriate interference similarity pair with the polynomial complexity and then optimize the radar task. Let us now focus on the code synthesis method. To this end, let us observe that the original design problem P1, which is in the left part of this slide, it is equivalent to the non-convex enlarged quadratic problem P2, which is given on the right of this slide. And it is obtained just reformulating the original similarity constraint, this one, as a homogeneous quadratic form. Specifically, it can be shown that the two problems are equivalent, which means that an optimal solution to P1 can be obtained from an optimal solution to P2 and vice versa. Now, leveraging on the equivalent matrix formulation of problem P2, where all the constraints can be written in terms of a rank 1 matrix, this rank 1 matrix here, and also neglecting the rank 1 constraint, we obtain the following convex semi-definite programming problem P3, which is denoted as enlarged quadratic problem relaxed. Notice that problem P3 is a relaxed version of our original problem because the feasible set of the problem P3 is larger than that of P2. And in general, the optimal solution of P3 might be not a rank 1 matrix. Nevertheless, we can prove that. First, the problem P3 is solvable. being its feasible set a compact set and the objective also a continuous function. Moreover, it is possible to prove that the relaxation is tight, in the sense that it is possible to construct a rank 1 optimal solution to P3 starting from an arbitrary rank optimal solution. This means that our original problem is hidden convex. Namely, it is equivalent to a convex optimization problem. The proof of this claim requires the use of some specific matrix, rank 1 matrix decomposition tools. And here we can see algorithm 1 that summarizes the procedure to select the optimal radar code. First of all, we need to compute the solution to the convex semi-definite programming problem. And this can be done, for instance, via the use of interior point methods. Then its rank is assessed. If the rank is 1, everything is easy. If the rank is larger than 1, then we need to call a rank 1 decomposition tool to obtain an equivalent rank 1 solution. And finally, in the last box of the scheme, a phase rotation is performed to comply with the original similarity constraint. And what is important to point out is the overall computational burden, which is connected with the implementation of the algorithm, is polynomial, as both the SDP problem and the decomposition can be performed in polynomial time. It is now time to assess the performance of this waveform design strategy. And in terms of detection capabilities, spectral shape, and also autocorrelation features, it is supposed that the radar system operates in the spectrally crowded environment, which is shown in the figure of the slide. There are 7 licensed bandwidths, which are displayed as the green boxes here in the figure, and all with the same relevance. And there are also 2 jammers, blue arrows, an electronic support measurement system can allow to acquire information about hostile jammers. In other words, we are in the presence of both cooperative and non-cooperative radiators in the radar bandwidth. And as a first step toward the synthesis of our waveform, in this figure, we can see the interference similarity achievable region for the case study at hand. The reference waveform is a standard chirp signal. All the points on above the boundary, all the points above this boundary, they correspond to a feasible design, and they are referred as operative points. The radar designer can choose the most suitable pair to trade off spectral coexistence, desirable radar waveform characteristics, and thus to indirectly control the achievable SANR of the system. For instance, small values of the parameters EI, they allow to emphasize the frequency coexistence of the radar with the overlaid telecommunication networks. And the operating points that we consider for our examples are those marked with the blue, the pink, and also the black colors. And the same level of spectral coexistence is enforced. And also the same yes, the same level of spectral coexistence is enforced. And here we can see the energy spectral density of the signals that are synthesized for the mentioned operative points versus the normalized frequency, and together also that of the reference code, which is the green curve. And you can notice that the reference code does not account for the presence of the overlaid radiators. And the stop bands where the license systems are transmitting are shaded in light gray. The curves highlight the capability of the proposed technique to control the amount of energy which is produced on the shared frequency bands. And for each similarity level, we can see that the energy transmitted in the stop bands is lower than the allowed level, and thus ensuring the coexistence with the other transmitting systems. We can also observe that increasing the parameter epsilon, according to the arrow here, I mean, we are augmenting the degrees of freedom that we have in our optimization problem. Smarter and smarter distributions of the usable energy in the spectral domain is achieved. There's also a progressive reduction of the radar emission in correspondence of the shared frequencies, as well as an enhancement in the rejection of the unlicensed jammers. As a result, we expect higher and higher SINR values. This is indeed shown in the figure that we can see here in the slide, when the normalized SINR is represented versus the parameter epsilon, and it confirms that the higher epsilon, the better the radar detection probability, being the higher the SINR. In fact, as epsilon increases, we have a higher and higher degrees of freedom in our optimization problem. And when the parameter epsilon is large enough, in our case, epsilon in the order of 0.7, the upper bound performance of 1 for the normalized SINR is achieved. Of course, to gain spectral coexistence, we have to pay something. There's a trade-off to consider. And in this plot, we can see the performance analysis in terms of autocorrelation properties of the designed waveform. We can observe that better SINR values, spectral compatibility, and interference rejection, they are swapped for worse and worse range resolutions and or integrated side lobe level or peak to side lobe level values. In fact, we can notice that increasing epsilon, we have a progressive reduction of the performance in terms of autocorrelation features. Let us now discuss an extension of the framework. According to the previous formulation, the radar controller could be enabled to deal with the design under the prescribed requirements when the desired operating pair lies outside the interference similarity achievable region. And to overcome this problem, the previous design strategy can be improved, allowing a suitable modulation of the transmitted waveform energy, which is no longer kept fixed, but is another degrees of freedom in our optimization. And this potential energy modulation can be accounted for through this constraint here, where the parameter eta is a design parameter, ruling the maximum allowable reduction of the radar transmit power, which can be set according to radar equation argumentations. I mean, it is possible to trade off radar surveillance coverage with the desired radar waveform features while fulfilling the spectral coexistence. This extension, this new algorithm is able to handle more stringent spectral constraints where the previous technique cannot be applied because of the incompatibility of the maximum transmit energy condition with the feasibility of the optimization problem. I will not go through the analytic details which are connected with this extension. They can be found in the papers that are quoted at the end of this presentation. I want to just mention that additional research has been conducted in this field to perform also a direct control on the interference power which is radiated on each frequency interval, so as to address a local control on each shared bandwidth, and also to account for constant envelope signals to comply with the amplifiers that are operating in saturation conditions. In general, sometimes it is not always possible to get the optimal solution to the optimization problem. Often the problems are non-polynomial hard. And what we can say is that in many situations, in polynomial time, we are able to find good quality solutions. And another important extension which is necessary to mention is the case of signal-dependent interference. Till now, we have focused on the case where the disturbance perceived by the radar is due to external interference sources like jammer or hot clutter. However, one of the major radar impairments is the self-induced clutter, which is a signal-dependent interference. And this is a very complicated situation because when we change the radar waveform, also the response of the environment changes. And also this case has been handled, and there are different solutions that are now present in open literature. Well, it is now time to go through the experimental analysis. A proof of the concept for spectrally compatible waveform can be found in the paper, which is reported in the blue box of this slide. Signals that exhibit a desirable spectral behavior and at the same time optimize the radar detection performance have been designed and transmitted. Two measurement setups have been considered. The former, measurement setup number 1, it is an hardware-in-loop approach without amplifier. And the measurement setup number 2, in air with a linear amplifier. We used a specific hardware-in-loop test bed to reproduce a kind of perception action cycle involved in the agile and the smart management of the radio spectrum, namely a spectrum sensing module to gather awareness about the surrounding RF electromagnetic scenario. This is the so-called perception stage. And then there is the transmission of a waveform fulfilling specific spectral compatibility constraints while optimizing the radar performance. This is the so-called action stage. The test bed is composed of a software-defined radio device to measure the actual spectrum occupancy, a standard personal computer, a laptop, which serves as digital signal processor to perform spectrum sensing and also to design waveforms complying with the spectral compatibility requirements. Then there is an arbitrary waveform generator to synthesize and transmit the desired waveform. And finally, a spectrum analyzer to measure the synthesized waveform spectrum and to demonstrate its compliance with the spectral constraints that have been forced at design stage, and also its fidelity with the nominal counterpart, I mean the waveform which is at the output of our MATLAB. I will not go within details which can be found within the paper I mentioned you before. I just say that we focused on a sensing bandwidth of 941 megahertz, and there are 4 licensed emitters as shown in the spectrum of these slides. The waveform has been synthesized for different situations about the tolerable interference, and the arrow of direction indicates that the system can tolerate lower and lower levels of interference. For each color, there are 2 curves, the solid and the dotted curve, which are the theoretical and the experimental. And you can see that there's a good agreement among them in all the considered cases. And in the measurement setup number 2, we compared the signal launched in the air for a short test with that measured in the hardware in loop experiment. And again, you can see that there's a good match between the nominal and the measured waveform. Actually, the amplifier was a linear amplifier in this measurement setup. And in this experiment, measurement setup number 3, we have assessed the effect of a power amplifier in the waveform transmission. And actually, the distortion could be significant. Please see the red curves in the energy spectral density. In this situation, a digital predistortion stage is often necessary before the transmission, but we can say that with a suitable design predistortion stage, we are still able to restore the original waveform performance and to respect the spectral mask. After the controlled experiments that we have seen in the previous slides, we were ready to test the approach on a real radar, and the ability of the waveform to detect both stationary and moving targets has been assessed using the PERSAX radar system, which is located at the Technical University of Delft. And here we can see the main characteristics of the PERSAX radar. It is an S-band, fully polarimetric and software-defined radar. It is also equipped with a multi-channel AWG. It is capable of operating in high and low power mode. There's 2 independent TX and RX antennas, and thus there are no blind ranges when used as a pulsed radar. Sorry. Well, and here we can see the reference waveform, which is a chirp signal with a pulse width of 50 microseconds and a bandwidth of 40 megahertz. There are 2 spectral constraints that are forced in the designed waveform, each of them with a notch of minus 35 dB. And if we run our algorithm in MATLAB, we obtain the waveform which is reported here in the bottom part of our slide. And we can see also the energy spectral density of this waveform on the right part. And this waveform has been loaded in the radar, and we are now ready to see the performance of the waveform when it experiences all the transmit and receive chain of the true radar system. We transmitted 512 pulses with a pulse repetition time of 200 microseconds, and we focused on 2 different scenarios. One, which accounted for a stationary target, and another one where there are many multiple moving targets. Scenario number 1, the radar has been pointed toward a calibration target, which is a stationary target. It was located at approximately 1.14 kilometers. And this target is a tall chimney made of 4 collocated pipes. You can see it also in this figure, which is reported in the slide. Of course, for this scenario, it is expected that the received signals are just delayed copies of the probing waveform. And once we consider all the transmitted pulse repetition times and we overlap the return pulses, we get the situation which is reported here. And you can notice that all the pulses arrives after a delay, which is a 7.9 microseconds, approximately at the range of 1.18 kilometers, which is the range of the chimney. As to the spectral behavior of the received signal, it is compared with that of the theoretical waveform and also the waveform which is at the output of the AWG. And you can notice that the depth of the frequency notches remains almost unchanged. And this indicates that the probing signal, which is transmitted in the open air and also experiencing all the transmit and receive chain, is capable to satisfy the constraints that have been set at design stage. Notice, for instance, the presence of non-idealities in the transmit and receive chain. Notice the behavior of the waveform here. There is some kind of attenuations in correspondence of these frequencies, and this is, of course, due to the real hardware of the radar system. And here we can see also the autocorrelation properties of the waveform and the fact that the signal experiences the non-idealities of the transmit and receive chain leads to a deterioration of the autocorrelation behavior. This can be seen from the higher side lobe level of the autocorrelation function. Here we can see the range profile in this figure on the left, and also the range velocity map. And the range velocity map confirms the presence of a target which is located at the range of the chimney and also a zero Doppler shift because it is a stationary target. In the scenario number 2, the radar has been pointed toward a highway, this position, for the segment of highway at approximately 4 kilometers. And on the highway, there are multiple targets. It is a 2-lane highway, and there are vehicles driving in both the directions of the highway. And here we can see the received signal, and here we can see also the compared spectral behaviors. You can notice that the received signal exhibit more complex structure than the previous case. And from the spectral behavior, we can notice that the depth of the frequency notches in the stop bands still complies with the spectral constraints that we have forced at the design stage. And the nice thing is the analysis of the range velocity map, which is this one, along the segment which corresponds to the highway. And the analysis of this map reveals the presence of multiple scatters that are moving towards and away from the radar, I mean, with positive and negative velocities. And their velocities are around 100 kilometers per hour and minus 100 kilometers per hour. And these are consistent with the highway segment, which is illuminated by the radar system. Well, I would say this is a good TRL level for an academic study. And now we are going in the last part of this talk, and Max is the speaker. Please, Max, the floor is yours.
Okay, let me share my screen. Okay. So thank you, Antonio. Let us continue the discussion with a different application, considering a cognitive jamming for selective barrage. So we have this term, selective barrage. What does this mean? Well, we have two concepts here. The first is the barrage jamming, which consists in the transmission of an interfering signal whose frequency support is much larger than the bandwidth of each radar or communication system in the scenario. And this involves the transmission of a noise-like non-coherent interference aimed at deteriorating the SNR of such emitters, preventing so data decoding, detection, or denying the accurate measurement of target information. So in this way, the jammer is able to mask multiple radar or communication systems simultaneously, as well as to mask a radar whose specific operating frequency is unknown. The other concept is the frequency selective. So if we consider a congested and contested environment, where both friendly and adversarial sources are present, so for example, radar or communication systems, in this context, we want to perform jamming while ensuring the spectral compatibility with the friendly emitters. And how we can achieve that? Well, this task can be accomplished by transmitting a spectrally shaped waveform, so transmitting energy only in some frequency intervals, as Antonio has explained in the previous slides. And to perform the selective barrage, we resorted to a cognitive paradigm, which consists in the implementation of the perception action cycle depicted in this slide. So with the perception stage, we recognize the presence of friendly or non-adversarial emitters within the bandwidth of interest. And this stage can be implemented by leveraging a library, providing the parameters of friendly emitters, and through an electronic support measurement system that analyzes the bandwidth, extracts the relevant spectral parameters, and recognizes the presence of friendly spectral activities. And in this regard, TR switch occasionally interrupts the jamming transmission to allow the ESM to monitor the radio frequency environment and perform the perception stage. As to the action stage, its goal is to actually synthesize and then transmit a jamming waveform capable of all interfering with the hostile infrastructure. So as previously said, this means to place some spectral notches where the friendly emitters are operating. And this slide summarizes this concept. So assuming that at the perception stage, we recognize the presence of a friendly emitter, in the action stage, our goal is to actually synthesize and then transmit a spectrally shaped waveform with a spectral notch where the friendly emitter is operating. Conversely, if at the perception stage we recognize the presence of two friendly emitters, then we synthesize we synthesize a waveform with two spectral notches. Finally, if at the perception stage we recognize the presence of both hostile and friendly emitters, then at the action stage we synthesize a waveform with only notches where the friendly emitters are operating. In this way, we are actually able to perform jamming on the hostile infrastructure while not interfering with the friendly communication or radar emitters. So it is clear that our goal is to actually design a jamming signal that aim at hindering the opponent sensing capabilities by reducing their SNR, but without interfering with the friendly emitters. And this goal can be accomplished by means of different approaches. So, for example, by resorting to a QC-QP-based approach design, as Antonio has explained in the previous slides, which allows to control the amount of interfering energy produced in the frequency intervals occupied by the friend resources. In this context, this approach will try to maximize the similarity between the jamming waveform and a noise-like signal C0. This is also tantamount to minimizing their Euclidean distance. Another approach that is possible to use, to consider, is based on simple orthogonal projection. So it is characterized by reduced computational burden, but at the expense of only being able to control the spectral notches' positions and width, but not their depths. So there is this trade-off between control and computational efficiency. And regarding this last approach, it is, as said, based on an orthogonal procedure where some spectral components at the frequencies belonging to the stop bands are removed from the reference signal. So formally, this means to project the reference signal C0 onto the subspace orthogonal to the steering vectors belonging to omega, which is the union of the stop frequency band, which is an info gathered from the perception stage. So the procedure to design such waveform is actually quite simple. Indeed, starting from the reference signal C0, it is possible to iteratively compute the spectrally shaped waveform by removing the spectral components at the frequencies belonging to omega. And in this expression, you can see this term PFI, which denotes the temporal DFT steering vector tuned to the frequency Fi. So while this method has the advantage of being computationally efficient, it provides less control over the waveform characteristics than the QC-QP-based approach. Okay, it's now time to discuss some numerical results for this application, and we considered a jamming bandwidth of 20 MHz, and we assumed the presence of 3 friendly emitters. This figure reports the normalized PSD of the several waveforms, and you can see 3 light gray rectangles, which denotes the stop bands. And for the synthesis of the jamming waveform, we consider the sequence length of 10 to the 5 samples, which means a 5 millisecond waveform signal. And for the synthesis of the jamming waveform, we used either the projection-based method or the QC-QP-based approach, considering block size of either 1,000 or 5,000 samples. This is just a slight modification to the original QC-QP-based approach, where instead of designing the whole waveform at once, we designed the subsequent block of 1,000 or 5,000 samples in order to reduce the computational burden. And for the synthesis of this approach, as Antonio has explained, we also can consider some notch depth, and in this case, we considered 16 decibel. And as said, this figure reports normalized PSD of the several waveforms. In particular, you can see the spectrum of the reference signal, which is characterized by, as expected, by a flat spectrum, because it is a barrage noise, so it is a noise-like signal. Whereas the other waveforms, so the waveforms synthesized via the QC-QP-based approach or the projection-based method, are characterized by these spectral notches, which are perfectly lined up within the desired stop bands. And notice also that the waveforms synthesized by the QC-QP-based approach are characterized by notch depth of around minus 60 decibel, which is compliant with the requirement, design requirement. Okay, we also carried out some experimental analysis for this application using an hardware in-the-loop testbed, And the aim of the experiment was to verify whether the interference injected by the designed jamming signal compromises the communication link of a friendly pi/4 deep QPSK communication signal. And for these experiments, we considered a central frequency of 1 GHz with a sensing bandwidth of 8 MHz. And basically, the experiment involved 3 main operations, which are the simultaneous transmission of the jamming signals and the frequency overlaid communication signal, then the measurement of the overall signal within the frequency band of interest, and finally, the evaluation of the error rate in decoding the communication waveform. And these slides, we reported an actual picture of the used testbed, which is composed of several software-defined radio devices, in particular an Adam Pluto device acting as a jammer, so used to transmit the jamming waveform, another Adam Pluto acting as the communication emitter, so to transmit the communication signal, then a mini circuits combiner to combine the jamming and the communication signal, and then a third Adam Pluto device acting as a receiver in order to collect the signal and store the data to a laptop for further processing. And these are the main results of the experiments. These are the PSD estimate of the measured data, normalized to their maximum value, and zoomed in for ease of visualization. However, before discussing these curves, let me zoom the figure again and put them on the site. Okay, so in this first figure on top, we reported the PSD of the thermal noise, which is this blue curve, as well as the PSD of the communication signal transmitted with an SNR of 16, 26, or 46 decibel. The other curves, the other figures, instead report the normalized PSD of the jamming signal plus the communication signal. And for the jamming signal, we transmitted either the reference waveform, which is this blue curve, or one of the waveforms transmitted, synthesized via the QCQP-based approach or the projection-based method. And each of these figures refers to a different case. In particular, this one refers to the case of communication signal transmitted with an SNR of 16 decibel, the second one with an SNR of 26, and the third one with the SNR of 46 decibel. And basically, we can observe that when one of the spectrally shaped waveform is transmitted, the communication signal, which is around 1 GHz and 2 MHz, does not experience any jamming interference. Indeed, you can actually clearly see its spectrum here. Whereas when the reference signal is transmitted, you can see that the communication signal is completely buried in the interference unless it is transmitted with a very high SNR, which is this last curve here, this last figure here. Okay, we also assessed the performance of the jamming, so the capabilities of the designed jamming signal onto the communication emitter in terms of empirical error rate. In particular, we, for each measured data, so for each scenario, we demodulated and decoded the communication signal, and then we compared the decoded information with the nominal counterpart in order to evaluate the empirical error rate. In this table, we reported the average error rates computed over 50 snapshots for all the several considered cases. Sorry. And basically, we can see that when the reference signal is transmitted, so when the barrage noise is transmitted, it is not possible to decode the information. Indeed, we have average error rates close to 50%, unless the communication SNR is 46 decibel, albeit with some error still present. However, when one of the spectrally shaped waveform is transmitted, then the resulting error rate is close to 4% when the communication SNR is 16 decibel, and it is 0% with when an higher SNR is considered. So this actually proves the successful cohabitation among this system. Okay, before concluding the presentation, let me show a very short video demo of the experiment. In particular, in this video, you can see two figures. The first figure reports the scatter plot of phase transitions between consecutive symbols. So it is the communication point of view. And you can see here there is a small number, which is the error rate, whereas the figure on the bottom reports the spectrum of measured data. And at the beginning, you can clearly see that there is the spectrum of the communication signal, so there is only communication signal transmitted, and it is possible to decode the information. And at some point, we will transmit the barrage noise. Here we are, and you can see that the communication signal is completely buried in the interference, and it is not possible to decode the information. However, when one of the spectrally shaped waveform is transmitted, if this is the case, you can see that now it is possible to decode correctly the information and so have the cohabitation between the jamming and the communication signal. Okay, it's now time to conclude this tutorial. So please, Antonio, the stage is yours.
Well, here again, we're ready to conclude this talk, actually where we have seen waveform design and diversity as a key ingredient to boost the performance of the next generation and possibly also cognitive radar systems in the presence of challenging spectrally crowded scenarios. We have seen the developments of effective algorithms to handle sophisticated waveform design problems. And Max showed you the concept of cognitive jamming. As a future research avenue, I would like to mention that it is necessary to put things together for a real-time perception action cycle so as to get higher and higher TRLs levels. And it is also important to consider the exploitation of other domains so as to achieve a better coexistence, such as the spatial, polarization, and also other domains. Please, Max, next slide. Here a selected list of references. Next slide. And also some books that we have produced during our research. And finally, please let me thank all of you for your kind presence. Let me thank also other two colleagues on my research group, Professor Augusto Bri and Professor Vincenzo Carotenuto. And last but not least, let me thank again Professor Antonio Capone for the kind and appreciated invitation. Thank you.
Thank you.
Thank you, Antonio. Thank you, Massimo. It was very interesting and very dense tutorial on this interesting topic.